Welcome to Binance Academy's intermediate course, Blockchain Deep Dive. This course builds on the knowledge you gained in our beginner course called Blockchain Fundamentals, taking your technical understanding to the next level. In this course, we'll study the core components underpinning blockchains, blockchain interoperability and scalability, as well as the blockchain's relationship with Web3 across 3 sections. In the first module of Section 1, we'll delve into the inner workings of blocks, which serve as the fundamental components of blockchains. But before we immerse ourselves in the details, let's begin with a brief overview of blockchain technology. Blockchain technology is a distributed ledger system that records transactions across a network of computers, utilizing cryptography to validate and secure data. It enables the exchange of data and digital assets in a transparent, immutable, censorship-resistant, and trustless environment. Blockchain also serves as the underlying technology for cryptocurrencies. The blockchain is made up of basic units called blocks that are chained together using cryptographic hash functions. The number of blocks in this chain grows as new blocks are added to it. To put this in perspective, as of April 14, 2023 at 5:50 p.m. UTC, the Bitcoin network reached block 785,390. This block number continues to grow as new blocks are added to the Bitcoin network approximately every 10 minutes. So, what's inside a block? A block typically contains a block header, a Merkle root, transaction data, and in some cases, additional information such as smart contract code. Let's take a closer look at each of these components. The block header includes metadata such as the block's version, a timestamp, the previous block's hash, and a nonce, which is a random number used in the mining process. All of this information is visible on Blockchain Explorer sites thanks to the technology's transparent nature. For instance, the block header of Bitcoin block 785,390 contains the previous block's hash. It's a 256-bit hexadecimal representation that looks like this. A Merkle root is a cryptographic hash representing a tree of all the transaction hashes within the block. Bitcoin block 785,390's Merkle root is a 256-bit output that looks like this. Each block also includes transaction data for the bundle of transactions recorded within the block. For instance, there are 3,264 transactions within block 785,390 on the Bitcoin blockchain. Some blockchains may include additional information, such as smart contract code. Now that we've taken a closer look at blocks, let's explore how they're chained together to form the blockchain. Blocks are chained together using cryptographic hash functions. Hash functions are mathematical algorithms that take an input and produce a fixed-size output. A cryptographic hash function can process input data of any size and type and generates a unique, fixed-length hash. You can think of them as fingerprints of datasets. Hash functions are generally deterministic, meaning the same input will always produce the same hash output. Hash functions are also one-way functions because it's computationally infeasible to arrive at the input data by reverse engineering the hash output. They are typically collision-resistant, meaning it's extremely unlikely to find 2 different inputs that produce the same hash output. The chances of a person being struck by lightning in a given year are roughly 1 in 1 million. The probability of a hash collision on Bitcoin is vastly lower than you being struck by lightning many times in a row. Lastly, even the smallest change to the input will result in a hash output that's drastically different. This is called the avalanche effect. Hash functions' deterministic, one-way, collision-resistant nature, coupled with the avalanche effect, underpin blockchain technology. You'll see how hashing works brilliantly to ensure a blockchain's security and efficiency as we go through the next few modules. The most commonly used cryptographic hash functions in blockchains are SHA-256, which is used in Bitcoin, and KEKAK-256 used in Ethereum. The way blocks are chained together is that each block contains the hash of the previous block, known as the parent block hash or previous block hash. The current block generates its own hash by applying a cryptographic hash function to its own block header, and this is included in the next block. This creates a continuous, linear, and immutable chain of blocks going all the way back to the genesis block, the very first block created in the blockchain. This chaining mechanism ensures the integrity and security of the blockchain, as altering the contents of a single block would change its hash, which would invalidate the previous block hash references in all subsequent blocks. To tamper with a blockchain, an attacker would need to modify the target block and then remine all subsequent blocks in the chain, which would require substantial computational power and immense cost, making it practically infeasible. Now that we've explored block structure and chaining mechanisms, let's focus on the three critical aspects of blocks: block height, block size, and block time. Block height refers to the position of a block within a blockchain and indicates a blockchain's length. The first block, known as the genesis block, has a height of 0, and each subsequent block increases the height by 1. For example, if a blockchain has a block height of 5,000, it means that there are 5,001 blocks in the chain, including the genesis block. Block size refers to the maximum amount of data a single block can hold. It's typically measured in bytes or kilobytes, and sometimes in megabytes, and determines the number of transactions that can be processed within a block. Block size directly impacts the transaction throughput of a blockchain network. A larger block size allows for more transactions to be included in each block, which increases the overall capacity and speed of the network. However, larger blocks also require more computational resources to process and validate. The reverse is true for smaller blocks, so deciding on the ideal block size is often a balancing act. Bitcoin was initially designed to have a block size limit of 1 megabyte. In 2017, Bitcoin implemented an upgrade called Segregated Witness, or SegWit, to improve transaction throughput. It increases the theoretical block size limit up to approximately 4 megabyte. Instead of a fixed block size limit, Ethereum employs a dynamic limit based on a parameter called gas limit. As of April 2023, the Ethereum gas limit is around 30 million gas per block, but this is subject to change. Lastly, block time refers to the average time taken to create a new block and add it to the blockchain. Bitcoin's target block time is 10 minutes, while Ethereum's is approximately 15 seconds. Block time affects the speed at which transactions are confirmed and impacts the blockchain's overall throughput. Let's conclude this module with a popular phrase among crypto enthusiasts: tick-tock, next block. As time marches on, new blocks are continually mined and added to the blockchain at regular intervals like clockwork. This process upholds the ingeniously designed blockchain networks that are transforming industries and societies. In the next module, we'll take a deep dive into how hundreds or thousands of transactions are authenticated and added to the blockchain.